The idea of including a third paper on regression in the MSc syllabus was to provide you an introduction to some extensions which we need for the linear model. Now, most of this paper covers the generalized linear model, where you have seen that the linear model is a special case, and the generalized linear model can be used to model outcomes which are not necessarily continuous. So for most of this paper, we have concentrated on modeling of counts, percentages, proportions, etc. In this module, I'm going to provide you a very brief overview of another direction in which the linear model can be extended, which is the generalized additive model. Now, from the name generalized, you can guess that we will consider a broad class of outcomes, the same class, in fact, which we consider for the generalized linear model, which is the one parameter exponential family with a scale parameter. However, in this case, the linear is replaced by additive. This means that we should no longer consider a linear predictor, or technically we will consider a linear predictor which is linear in the parameters but no longer linear in the outcome. I'm going to introduce the generalized additive model starting from some examples which may be more familiar to you, and then work on introducing the concept of smoothing. We will introduce the concept of smooth versus rough. We will look at how to quantify roughness in a regression example. We will look at alternative methods of smoothing. We will also introduce the concept of spline, which is used commonly to model regressions. You may have heard of something called the broken stick regression model, which can in fact be fitted within the purview of the linear model, and we shall see why the answers from this can sometimes be questionable. We shall introduce briefly the concept of penalized regression models. And all in all, I hope you will get a sense that the amount of smoothing is really a very critical parameter, and it is necessary to spend some time on choosing this, and also that not necessarily all criteria which we use to choose the amount of smoothing will lead to the same answer. The generalized additive model, or as it is more popularly known in the statistics literature, the GAM. It is a generalization of the linear model as also of the generalized linear model, where we continue to model outcomes which can arise from the exponential family. So this means that it can refer to continuous outcomes, discrete outcomes, proportions, counts, and so on. The word linear has been replaced by additive. So let me first try and give you an explanation of additive models, and I will try to motivate it by relating it to concepts with which you might already be familiar. So the first related concept with which you might be familiar is the idea of polynomial regression. We see a scatter plot in this example where we could fit a linear model, but there is some indication that the slope first reduces rapidly, then starts to stabilize, and after a certain point again starts to fall. This kind of regression cannot really be captured by fitting a single linear model, by fitting a single line, and instead a better idea would be to fit quadratic regression. So here we would try and fit the line y equal to a plus bx plus cx squared plus error. Now, as we know, the linear model can accommodate any model which are linear in the parameters, and we do not really need linearity in the covariates. So this is something which can be fit well within the purview of the linear model. However, the answer here is not necessarily desirable, and the reason is the fit can be unstable. As you are familiar with the concept of multicollinearity, I can say that polynomial regression leads to regresses which are very highly correlated. So for example, if I use functions like 1, x, x squared, x cubed, and so on, these could be very highly correlated, leading to multicollinearity, and we know that the consequence of multicollinearity is unstable estimates. Another consequence of multicollinearity and polynomial regression is that this resulting fit is highly sensitive to outliers. So the presence of outliers in the data would lead to a fit which was very highly influenced by whether or not you chose to include the outliers in the regression. However, this is a good starting point to explain the concept of generalized additive models, and it motivates the concept of smoothing. Here is a second example with which you might be familiar. So this is a time series data set where I'm looking at the price of a commodity by day. In the first row in this data set, I have looked at the date, starting from 24th March 2010, and in the second column, the price of a commodity. In the remaining three columns, I have smoothed out the data by taking something called a moving average, which is I decide on a certain length of averages and I continue to take local averages of the data, leading to a moving average estimate. So here is a plot of my original time series in black, as well as plots of two moving averages of different periodicities. Now you can see that the plot of the raw data fluctuates a lot, while the plots of the two moving averages are considerably smoother. So again, this is a good point for introducing the concept of smoothing and why we would look for smooth answers in any particular situation. A third motivating concept with which you might be familiar is the idea of kernel smoothing. So here I'm trying to fit a regression yi equal to m of xi plus epsilon I. M is a function of x, but it is an unknown function of x, and I make no assumptions about m except that it is a smooth function of x. One way of getting m hat hx is first to choose a value of h, next to choose the function k, which is called the kernel, and to take the average which we see in the second line of this slide. So if you look at this equation, it's a simpler way of putting it. It tells me simply that my predicted value at the covariate value x is a weighted average of all the data. However, the weight given to the value of xi depends on the particular location where I am at. A very common choice for the weight is the normal kernel, in which case kh of x minus xi would be replaced by the normal density, which is centered at x and has a variance of h. As you know that the shape of the normal density varies with the scale parameter, here h is a function which controls the length of the period over which I am taking local averages. So here are the results of 4 kernel smooths applied to a data set. You can see while they are generally similar in that they are both, all 4 of them are generally increasing, there are some differences in terms of how much structure they pick up from the data. The 4 plots are indexed by 4 different values of h. In the first, h is really small, which means that averaging is over a very small window, and a lot of importance will be given to any local fluctuations. This is why the resulting fit from this fluctuates more and is rougher than the remaining points. As I gradually increase h, the function becomes flatter and picks up less structure from the data. So h is one example of what is typically known as a smoothing parameter, and as we shall see in all subsequent examples, the choice of the smoothing parameter is a very critical decision and it affects the conclusions that we draw about the predicted model. So more generally, we can define something called a Loess smoother. Note that linear regression assumes that the relation between x and y is linear, or if not linear, if it could be polynomial, but it is necessarily monotonic and constant across the domain and range of each variable. Now, there is no reason why every single regression must be linear or polynomial, or in fact even have a particular structure like being monotonic. To some extent we can address this using polynomials, but as we have seen, polynomials are not always desirable in terms of properties of the model fit. A better generalization is to use the Loess smoother. Now, as with kernel regression, the Loess smoother says that there is no restriction on the functional form between x and y. So the functional form could be anything. There is only one restriction, which says that the functional form has to be smooth. So this means if there is no restriction, it means that we have less information and the fits must be more computationally intensive. If done properly, we can get extra information from the data, but just as with kernel smoothing, the information that we get is highly dependent upon correct choice of the smoothing parameter. So the name Loess actually stands for locally weighted least squares regression, and in many software versions you can get an additional function LOWESS as well as a function LOESS, both of which affect Loess smoothing, but there are some minor differences between the two. The idea behind both, of course, is to use more local data to estimate our y variable. Say we have a point x on this slide, say the value 2000, and we wish to predict y at the value x equal to 2000. The idea is that I would take an average of the data, but it would not be a simple average but a weighted average, and it would give more weight to points in the vicinity and less weight to points which are far away from the vicinity. This general idea is referred to as Loess smoothing, and a particular example of this is kernel smoothing. Loess smoothing has its problems. So here is another example of Loess smoothing where the resulting line does not capture a lot of the fluctuations of the data. Yet another example of Loess smoothing fitted to the same data set, and here it seems to be a trade-off between the earlier 2 points in that it captures some of the variations and it does not capture the rest. So as you can guess, these 3 examples refer to 3 different choices of my smoothing parameter. In this case, the weights and the window which I use to effect the smoothing, and the final predicted value which I get is highly dependent on my choice of this smoothing parameter. Let me introduce a concept called splines, which will make it easy to introduce the generalized additive model. Spline is a term which comes from engineering. You may have heard of engineering splines. Splines is used extensively in statistics. There are many different kinds of terminology. There are regression splines or smoothing splines. The simplest example of spline regression is something called the broken stick regression model. The broken stick regression model is something which can be fitted directly using the linear regression techniques which you have heard before. So why would we use something called broken stick regression? Now recall that when we fit a line to a scatter plot, we are assuming that the slope of this line remains constant throughout the range of the dataset. Now there is no reason why this should hold, and it might be that the slope varies in different neighborhoods of the predictor. When this happens, the regression line looks like a broken stick, and hence the name. So here is an example of a broken stick where up to the value of about 10, my predictor is increasing at a very fast rate, and beyond the value 10, it is still increasing linearly but at a relatively slow rate. As I said before, broken stick regression can be fitted using the linear model. So instead of using a covariate x, I will fit a regression of y on a transformed covariate. Let me define x1 as equal to x if x is less than equal to k, and k if x is greater than k, and x2, which is 0 if x is less than equal to k, and x minus k if x is greater than k. Then a good example is for you to check that the broken stick regression can be fitted by fitting a regression of y on x1 and x2 using the equation given on the last line of this slide. Now in the broken stick regression, we have assumed that there are two components to the slope. More generally, the slope may vary much more across the range of the data, in the sense that we might be able to break up the data into B subsets where the range is constant within each subset but different across subsets. Now again, it is possible to fit this model using a linear model, and it is a good exercise for you to check that if we define transformed covariates xb, where xb is 0 if kb minus 1 is greater than x, equal to x minus kb minus 1 if kb minus 1 is less than equal to x is less than kb, and equal to kb if x is greater than kb, then fitting the regression of y on x1, x2 to xb minus 1 will indeed result in a piecewise linear model. I should mention here that k1, k2, k capital B are points which are called breakpoints, and they correspond to the intersecting points where the slope will change. We assume that these are known and do not have to be estimated from the data. We can generalize this idea further and say that there is no reason why the regression has to be linear within each set of points. So, just as we can define a piecewise linear spline, we could also have piecewise polynomial splines. And in fact, the definition of spline in the statistics literature is piecewise polynomial functions. This slide shows two spline models fitted to a regression. The first is a linear spline, where within each interval of knots, the spline is a linear function. The second is a quadratic spline, where we have allowed each of these segments to have its own separate quadratic regression. Note, however, that the quadratic regressions have been chosen so that there is no jump when we go from one interval to another, and the connection happens smoothly. So again, splines are piecewise polynomials. They're very easily generalizable from the definition we have given before of piecewise linear functions, and again it is a good example for you to check that the piecewise polynomial regression can indeed be fitted within the purview of the linear model using the model equation given on this slide. Just as in the case of low S or in the case of moving averages, we have had to deal with the question of how smooth we want the answer to be. Similar questions will arise for spline regression. So on this slide, you see two panels of plots with two different smoothing parameter choices for spline smoothing. The first is a very rough plot, in the sense that it almost practically interpolates the data. The second is a very smooth plot, and it tends to ignore the pattern in the data at the cost of giving a smooth answer. So what is the trade-off between making a choice between these two plots? In the first case, we have picked up a lot of features of the data, but this means that while the answer will give a very good fit to the data set at hand, for a future data set in which the errors will be different, the quality of the prediction might not be that good. The second plot, it will give a reasonably good answer for subsequent data sets, but the fit to the data set at hand is not really that good. So there is a trade-off, and again we can see that the choice of the smoothing parameter has a critical bearing on the answer which we get from fitting this model. So 2 more examples which further illustrate the question of how smooth we want the resulting lines to be. Again, we see that the first panel, we have done something called over-smooth the data, which is we have ignored a lot of the features which appear to be present in the data. And in the second, we have an answer which picks up a lot of the local features. Now, is it really picking up local features or is it picking up noise, in the sense that would these features be replicated if we were to get a second data set? These are all very tricky questions which you have to deal with when you perform smoothing. So how smooth is our answer? In the case of the models we have considered so far, it is driven by the number of knots. It's also driven by the nature of piecewise functions, which we call basis functions in the smoothing literature. So a quadratic spline would be smoother than a linear spline, but there is a trade-off because a quadratic spline would also introduce more parameters than a linear spline. The general broad directive is to select the amount of smoothing so as to minimize a criterion called the prediction error. However, as different statisticians measure prediction error using different criterion, you could, for example, use the Mallows CP, or you could use the AIC, or you could use something called the GCV, the generalized cross-validation. And there really is no guarantee that in every case you will get the same answer for the optimal amount of smoothing. So this is to drive home the point that the choice you make of the smoothing parameter is a very, very critical decision when you try to perform statistical smoothing. So far, the results we have seen can be fitted within the usual linear model. In this slide, we can see 2 plots. The one to the left has been fitted by using the linear model and spline regression. The second has been fitted by using something called the penalized spline. At a glance, we can see that the results we have gotten in the second panel are a lot smoother than the results which we have got in the first panel. Below the plot, we can see a plot of lines, and these you can satisfy yourself are what the basis functions for these 2 examples look like. So what really is the difference between these 2 plots? Penalized splines allow automatic data-driven selection of the amount of smoothness. This means that we do not have to pre-select how smooth we want our answers to be. So even though we have chosen a certain number of knots, that does not constrain the smoothness, and we have an additional parameter which measures how smooth the results will be, and we have a means of selecting this parameter optimally. So the idea is that unlike the regression splines, we no longer minimize the least squares criterion, but we minimize the least squares criterion subject to a roughness penalty. So this is what my criterion looks like. The first is the usual least squares. So yi minus f of xi, where I'm trying to fit the regression yi equal to fxi plus epsilon I. The first term is the usual residual sum of squares, but I have also added a second term, which is a multiplier h times an integral f double dash x whole squared integrated over the range of x. This second term is called a roughness penalty. Now recall that a linear function is smooth. If we want to penalize departures from linearity, we can do so by penalizing the second derivative of the curve. So the second derivative would be exactly 0 when we have a linear answer, and it would be different from 0 the further we go from linearity. So the squared integral of the second derivative is considered a good measure of how rough a curve might be. So our optimizing criterion is now the sum of squares plus a coefficient times the roughness penalty. This coefficient, which here has been denoted by h, is the smoothing parameter because it controls the importance which is given to the roughness penalty. If h is large, then more importance is given to the roughness penalty than to the least squares, which means that we will get answers which are very smooth, answers which will minimize the roughness penalty. If h is small, then the roughness penalty will not really matter, and we will tend to get answers which minimize the least squares criterion, and these will be more rough. So in a nutshell, parameter estimation and inference for these two kinds of splines. For regression splines, they continue to be the usual linear model, and inference estimation, it's all based on the usual least squares theory. For smoothing splines, the model is still similar, but we introduce an additional parameter. We can show that it has a connection with linear mixed models rather than linear models, and estimation is based on minimizing the prediction error. So the smoothing parameter is chosen so as to minimize the prediction error. Very briefly, let me introduce the idea of generalized. So far I have been considering continuous outcomes and trying to motivate the concept of smoothness. The generalized model, the generalized additive model, follows very closely. So in the first line on this slide, I have written the additive smooth equivalent of the logistic model. Now note that for the usual logistic model, probability y equal to 1 given x can be written as e to the power x beta by 1 plus e to the power x beta. Written in a different way, this says that log of probability y equal to 1 given xi by probability y equal to 0 given xi is equal to x beta. That is, the log odds of y equal to 1 is linear. If I were to perform the same transformation on this data set, then I would get log of probability y equal to 1 given x is equal to f of xi. My assumption about f is that it is not linear. In fact, it does not need to have any specified form. All I postulate is that the function f must be smooth. So we have almost defined the generalized additive model. The model which I have shown in my earlier slide has been applied to a dataset predicting union membership with wage. In the first panel, I have shown a scatter plot of the data, and unlike with continuous data, the scatter plot is not helpful at all because the outcome union membership, yes, no, it clusters at two values, 0 and 1. So we cannot really visually smooth the scatter plot as we have done for the case of a continuous outcome. However, I can continue to use the idea of spline regression, and here is the answer from this fit. Now in this very last slide, I will finally define generalized additive models with the help of an example. So here I continue to want to predict probability of union membership given information on several covariates, which is wage, years of education, age, whether or not female, whether or not white, whether or not from the South, for a dataset which originated from the US. So as before, I'm writing the logit of this probability as a function. So this function comprises of an intercept beta naught plus usual terms beta 4 into female plus beta 5 into white plus beta 6 into South for the last three covariates. However, for the first three covariates, wage, years of education, and age, which are continuous, I do not have the usual coefficient into covariate. Instead, I have replaced these by F1 of age plus F2 of years of education plus F3 times F3 of age. So the functions F1, F2, F3 are not assumed to have any particular form, they're only assumed to be smooth. Because I have three separate functions for three separate covariates, and they figure in the logit of the model as a sum F1 of wage plus F2 of years of education plus F3 of age, this motivates the idea of additive. So the effects of the covariates are additive, which explains the additive part of the GAM. I'm looking at generalized outcomes, which explains the G part. So this is one example of a GAM. Fitting is of course a lot more complicated because we now need to jointly estimate the smoothness in various directions. Covariates might be correlated and so on. However, this is as far as we are going to get in this paper, and if you are further interested in fitting GAMs or knowing more about the theory, you can look up the references which have been listed for this module. To summarize, in this module, I have introduced the concept of a generalized additive model, or a GAM. Now, this is a kind of different direction in which we can extend linear models, different from the idea of going from a linear model to a generalized linear model. Here we still continue to look at generalized outcomes, which is we still consider outcomes from the one-parameter exponential family, but we replace the concept of linearity with the concept of additivity. In this module, I have tried to motivate the concept of additivity, starting with concepts with which you might be familiar, such as low S, or kernel smoothing, or polynomial regression, or even moving averages. We have generalized this to the idea of a spline and seen that spline-based regression models, which include the broken stick example, can be fitted either within the purview of the linear model, in which case we really do not need any extra kind of methodology, or they may be fitted in a better way using something called penalized regression. An important message from this module is that the answers which we get from smoothing are always conditional on the way in which we choose the amount of smoothing, and this is a parameter which has a critical bearing on the inferences which we make from the data. Now, in general, we use prediction criterion to choose the optimum amount of smoothing, but then there are also several choices of prediction criteria available, and it is not necessary that all choices of criterion will always lead to the same answers.